We are back, and we have our second panel of the day, which is Advancing Readiness. And I'm going to just go ahead and let Dr. Harri Vanhala kick off for us. Thanks.
All right, thank you very much. You get the slides?
You can click it.
Okay, there we go. Thank you very much. My name is Harri Vanhala. I am with the NASA Space Technology Research Grants Program, which is at the STMD. And I'm very excited to moderate this panel where we have three great presenters talking about three exciting projects. So we're looking forward to it. Just a couple of words about the program from which this project are from. So Lunar Science Technology Research is at STRG, and the purpose is to have universities lead efforts that are short in duration, fairly high impact, so quick, significant impact on lunar surface technology development. They are university-led projects, but they can have teaming with other universities, nonprofits, and industry. These are early stage technologies, so starting TRL is fairly low, but we do ask everybody to consider post-infusion as an important aspect of their projects. And that's why we're presenting this project to you today, to let you know of them and see if there might be some collaborative opportunities as these projects head toward the end stretch. So they're at about 1.5 years into their couple of years of project duration. If you want more information on LuSTR, there's a QR code and as well as the URL. So we have three exciting projects today. One LuSTR, Christine Hartzell at the University of Maryland dealing with dust mitigation. Cynthia Song at the University of Pennsylvania, which deals with robot collaborating on the lunar surface. And finally, Christopher Dreyer at the University of Colorado School of Mines, which handles ISRU. And without further ado, I'll turn the podium over to Christine.
All right, thank you. Okay, great. So I'd like to start by acknowledging the pretty large group of people that have been working on this project. We have research scientists, postdocs, grad students, and undergrads all working on this project, along with our technical point of contact from Goddard, Tina Montegarcia. Okay, so the technology that we're trying to advance is basically developing a lint roller for the moon. All right, so we would like to be able to remove dust from spacesuits as well as hard surfaces like solar panels using a technology that is actuated just like a lint roller. But instead of your traditional adhesive, we're replacing that adhesive with a synthetic gecko skin membrane. This is a membrane that is fabricated out of silicone. You can see an SEM image there in the bottom right corner that shows these kind of ridges on the surface of the membrane. And these are 10 micron scale type ridges that increase the surface area of that membrane and thus allow it to stick to different surfaces and in our case pick up dust. So the Gecko technology, or Gecko skin technology, has been used for a variety of different robotics applications, but the downfall of its use in robotics is that it gets dusty and then it stops picking things up. So we are basically exploiting that tendency of the gecko skin to adhere to dust. Synthetic gecko skin can be purchased or you can make it in the lab, which is what we do. And this technology could be actuated by an astronaut using it just like a traditional lint roller or by a cleaning robot. Imagine a Roomba driving around a surface where its active surface was this gecko roller. It does not require any power to remove dust from a surface, but we do require power to make that gecko skin reusable. So rather than bringing multiple sheets of this membrane to the surface of the moon, instead we're also trying to develop a mechanism to clean the gecko skin. The con-ops here is that your astronaut would have the gecko roller when they're out on their EVA, clean off whatever surface or spacesuit needs to be cleaned, and then when they return to the habitat, they insert that gecko roller into a cleaning appliance, and it becomes reusable. We look at two different technologies to clean the gecko roller. One is by embedding an electrodynamic dust shield underneath the gecko skin, and the second is just by spinning it really fast and using those centrifugal forces to kick the dust off the surface. Okay, so the objectives of our LuSTR project were to identify basically the key performance parameters at laboratory conditions and then look at the performance in more environmentally relevant conditions like ultra-high vacuum and also low temperatures. We also want to investigate the efficacy of cleaning the Gecko roller and determine if that is really an advantageous route to go down, or if we should view these more as disposable technologies. And then we're also looking at a prototype sensor that would indicate when the roller itself is saturated with dust and needs to be cleaned or replaced. This is a schematic of the test stand that we use to test the efficacy of the roller in laboratory and thermal conditions. What we have here is a platform, which is where we sprinkled the dust. Then we have a roller where the gecko skin is adhered to. There's a stepper motor that controls the translational motion of the roller across the test stand. And then we're also able to apply different weights to the roller to control the downwards pressure on the roller, which is one of the characteristics that we're interested in exploring for this design. In order to control the amount of dust on the surface, we have basically a small slide that we slide across the surface and ensure a uniform distribution of dust across our surface. For the results that I'm showing here, we're looking at about a 3 dust diameter thick layer of dust on the surface that we then try to remove. Here is a video of our Gecko roller in action. The roller is going to be moving from left to right across the screen. On the right side, you can see kind of this white appearance. That's the dust. We use Lunar Highland Simulant 1 from the Exolith Labs. And then you can see an encoder that measures the slip of the roller, because we'd like to actually be rolling rather than pushing the dust across the surface. And then we have these 2 sort of saddlebags that are holding weights controlling that downwards force on the roller. So we're going to see the roller move from left to right. And you can quite clearly see that there's this darker region. That's where the dust has been removed. And then on the top and bottom of the screen, there's this undisturbed dust that has not been impacted by the roller itself. So that's what the roller looks like in action. We have characterized how much dust is removed as a function of the downwards force. So this is in 1 revolution of the roller, we're seeing up to about ½ a gram of dust removed off of the surface when we have this about 3-layer thick amount of dust on the surface. We also characterize the slip of the roller. We can see that at low downwards pressures, there's increased slip. This makes sense, and it's probably due to issues with ensuring that the roller and the sample plate are perfectly level. The image on the right is an SEM image of dust adhered to those little wedges on the gecko skin, and you can see that the dust is quite a bit larger than the wedges itself, so it's not really embedding between the wedges. In our future experiments, we're going to be looking at the LHS-1D, or the dust simulant, which has a smaller particle size distribution, and we'll see how these results change for those smaller particle sizes. Our next steps are to look at doing ultra-high vacuum testing. So we're talking about sub-nanotorr vacuum testing levels. And this is quite a challenge when we're thinking about dusty vacuum chambers, dust in a vacuum chamber at these very low temperatures, or very low pressures. So we, one of the ways that we're trying to avoid getting dust into our turbopump is by actually mounting the turbopump at the top of the vacuum chamber to try to have gravity work with us and prevent the dust from getting into the vacuum chamber. We're also planning on baking out the whole system, and all the pieces of this system have been ordered. Many of them are in the lab, and we're starting the assembly. Here's a look at the test stand that's going inside the vacuum chamber. In this test stand, rather than moving the gecko roller itself, we're moving the dust underneath the gecko roller. So the vertical shaft there controls the downward pressure and downward location of the roller. And then we have a sample plate that translates underneath the roller and also presents the roller to the loading door where we can refresh the sample between experiments. Now, one of the challenges of doing this ultra-high vacuum testing is that the silicone that we use to make gecko skin has not been tested according to NASA standards at these very low pressures. So that testing is ongoing now. There are other silicone elastomers that are NASA vacuum rated, but we haven't made gecko skin with them. So we have a couple of options here. We're not sure what we're going to end up with in terms of the material that we use for the gecko skin. We're also planning to do thermal testing. We're very interested to make sure that this gecko skin works at low temperatures. One concern is that these small wedges may become brittle at very low temperatures, which would then decrease their ability to conform to variations in surface roughness, which would, of course, decrease its efficacy. Now I'm going to start talking about the different methods of cleaning the gecko skin. So we've talked about how we're going to assess the efficacy of the gecko skin performance under normal conditions. Now, can we make it reusable? So the two methods that we're exploring to make it reusable are first, embedding an electrodynamic dust shield underneath the gecko skin, and then second, basically just spinning the gecko roller very fast. So I don't think I need to go into a whole lot of detail about EDS functionality here, but in short, we are using a three leads in a square spiral. That's the form factor of our EDS leads. And this is just laboratory conditions where we have EDS, gecko skin, and then the dust itself. So we are loading the dust onto the gecko skin in the normal way that it would actually be actuated. And this is a video showing the dust being removed from the gecko skin using the EDS. So EDS, always very pleasurable to look at, very effective. So it works even when it's embedded underneath a gecko skin. Here's our design for our rotational cleaning test stand. Again, we're just spinning the roller very fast about its axis. And we have this test stand to ensure that our dust will be contained in the appliance. We can control the speed of the roller, and we're making sure that we're not going to be inhaling any of our simulants. So in terms of TRL status, the initial was initially when we wrote the proposal. Current is our current state now. So we have shown that the Gecko roller is quite effective at picking up dust off of hard surfaces. We did some initial work looking at ortho swatches, but we haven't repeated that using simulant yet. The EDS cleaning appliance is also quite effective at removing dust from the Gecko skin. The rotational cleaning appliance, we're still building up that test stand, but we have demonstrated it at a lower fidelity and also seems to be quite effective at removing dust from a surface. So in summary, the Gecko roller is a dust removal technology that requires no power to remove dust from a surface and can remove about 0.5 grams of lunar regolith per revolution of this roller. And to give you an idea of size, it's just the same size as your typical lint roller. And the roller can be made reusable via cleaning in a specialized appliance, either via EDS or high-speed rotation. And we're planning to do ultra-high vacuum and thermal testing this calendar year. In terms of partnership opportunities, we'd be interested in doing additional testing with optical surfaces, spacesuit materials, also help making new gecko skins molds. These molds are actually quite difficult to make. And then, of course, testing in situ would be the ultimate goal. So thank you.
Thank you. And next we have Professor Sung, who I believe is online. Cynthia?
Yes, hello. Can you hear me?
So we need to advance slides.
All right. Thank you. I'm sorry I couldn't join you all in person. This conference coincided with another one of my, some bit of travel, so I'm not able to join you there, but I'm really excited to share the work that we've been doing in the TRUSSES project, and in particular, a multi-robot collaboration for being able to navigate extreme environments. And so if you could go to the next slide. The premise behind this project is that lunar environments are sandy environments, which are very difficult to traverse. What you're seeing here is a video of a legged robot, which people would consider pretty agile and maneuverable, but on these sorts of sandy environments, there's a lot of slippage, a lot of sinkage, and over time, errors accumulate in the robot's ability to do pose estimation, the control goes unstable, and the robot tips over. This isn't just a controls problem, but also a mechanics problem in the sense that this kind of uneven slippage and sinkage is currently relatively unpredictable, but also there are situations where the ground might be so hazardous that the robot is going to get stuck. And so the idea behind our project is to be able to deal with these sorts of situations. So if you go to the next slide. This is an overview of our different areas of research. We want to investigate how heterogeneous teams of robots can jointly overcome environmental hazards such as sandy environments, and slippage and sinkage traps. So our project consists of two major components. If you click next, our first component is that we want robots to be able to measure and then use those measurements for planning ground interactions as they move around. One of the folks on our team is a geophysicist. He's interested in measuring reaction forces from ground penetration. And so we've been looking at how we can take those measurements and then directly convert them into models. At the same time, if you click next, we're interested in how robots can do these sorts of measurements on the fly. So as robots are going about their normal regular missions, they can take sensing measurements that allow them to build these models. If you click next, then the second part of the strategy is that we want to be able to take these models and use them for planning. And the project is built on this hardware platform that one of our team members has created, which is basically this extendable arm that we can use to connect robots to each other in order to be able to produce pushing and pulling forces and assist and allow robots to assist each other to be able to traverse hazards. So the final component, then if you click next, is the planning. And so taking advantage of the models that we're and measurements that we're taking in strategy one, along with the particular hardware platforms that we're developing, we want to be able to then figure out how we can plan motions for these multi-robot systems to be able to rescue robots when they are stuck and also potentially preemptively deal with those situations. So if you click next, I'm going to lead you through our major results in each of these different areas. The first is that we've been doing quite a bit of work in trying to characterize the behavior of LHS-1 simulant, which you heard a bit about in the previous presentation. What we've been doing is looking at what the ground reaction forces might be when a robot comes into contact with the surface. And in particular, the ground basically has a stiffness that is dependent on the packing density of the ground. One thing that we found, which is very interesting, is that because LHS-1 has a very large range of particulate sizes, actually the range of stiffnesses that you might find in a bed of LHS-1 is much larger than what you would find like on the beach or in spherical beads, for example. And so we've been trying to compare the measurements that we can take in the lab on campus, where we filter out all of the fine particles, as well as in the survey testbed, which I'll show in a minute, and where they don't, to see what are the differences between the behavior of these sorts of grounds when you have these different particulate sizes. What you're seeing in this plot, though, is two examples of the force displacement curves for the ground, and you're seeing a pretty linear relationship between the normal force from the ground and the penetration. And this is something that we can measure on the fly as robots are moving around on the surface. So if you click next, one of the things that we've been doing then is trying to do those on the fly measurements. This video should be playing. Maybe if you click next, it'll play. Yes, okay. And so what we find is that when you have robotic systems that have motors with relatively low gear ratios, then actually the current signal in the robots is a measurement of force. And so as robots are navigating over these environments, naturally they get force measurements from their contact with the ground, and we can use those measurements to take on the fly, to build maps on the fly of these environments. So here you're seeing some examples of these real-time force measurements that a Leggett platform is taking, which we then took to the AIM survey testbed, which you can see on the next slide, to see whether or not these algorithms are useful in real-life environments. So we've been working with people at AIMS to try to do these tests. And if you go to the next slide, you'll see this setup where we have now this robot walking around on this testbed, where we've changed the, we've manually constructed this environment where there are pockets of packed ground. Those are the red regions you see in the picture in the middle, and loose ground, that's the blue regions you see. And as the robot is walking over this environment, it is taking force measurements at the toes. Using that information, we can now reconstruct a map from the robot's walking, which is the map that you see on the right. And you can see that in terms of stiffness patterns, we get something very similar in the measurements as what we originally constructed. This is really useful, we think, because if you go to the next slide, what we can do is convert these maps into predictions of risk. And so we have some models for being able to extract from the stiffness of the ground and also the mass and the joint motions of the robot, what their predicted velocity in the ground is, and whether or not they'll slip and therefore have zero velocity, or whether they'll have enough traction to be able to move forward. What you're seeing here is the map that we constructed from the survey test converted into these velocity maps, which now we can start to use to construct obstacles as risk and do planning on. So if you go to the next slide, then if we want to move into areas that are hazardous for these sorts of robots, and we predict that they aren't going to be able to move reliably at all, we want to be able to create larger truss structures so that they can be more stable. If you click next, the video should play. And we're building these ideas on a hardware platform called the Spiral Zipper Arm, which is this extensible arm that can carry loads up to several hundred newtons. We can use this arm then to connect multiple mobile robots to each other to be able to create these leverage forces. And so if you click next, what we're doing now is modeling these sorts of truss structures as spring networks that allow us then to predict the displacements of these systems as these arms extend, while taking into account the ground reaction forces that we've measured on the fly. So if you click next, then again, we did some of these tests at the AIM survey testbed. If you click next, yes. And what you're seeing here is some of our preliminary experiments using the spiral zipper arm to drag first just a box around in the bed and measure the reaction forces from the ground to make sure that they match the models that we've created. What you're seeing on the right is the force that's being exerted from the arm as this box is transitioning from hard ground into soft ground. And what you'll see is that the reaction forces are actually larger in the soft ground. This is because, if you click next, there is buildup in the material as the robot is being dragged around. This bulldozing effect is something that we do need to take into account in our planning algorithms. So to show you then our final, our system so far, if you click next, this is our current multi-robot setup. We have a two robot, in quotes, system where we have this mobile robot connected by a spiral zipper arm to this box with legs, which we're using to simulate another robot. You're seeing that the wheeled robot is able to drive forward. We're also able to move, contract the spiral zipper arm. When that happens, then the way that the system displaces depends on the specific ground robot interactions. So what you're seeing in here is that actually the legs on the box are able to anchor that box into the ground and drag the wheeled platform backwards. What we've also seen is that over time, through repeated tests, that the wheeled platform starts to pack the ground. And at some point, you start to gain traction and allow the robot to move more effectively. But after a certain amount of time with too much packing, then actually this hard surface becomes much more difficult to traverse. And trying to navigate how what happens as robots repeatedly traverse these sorts of environments can also be taken into account in these ground models. So if you go to the next slide, over the course of this project, we've had various conversations through LSIC and through LPSC to try to understand what the specific use cases are for the system. I think that what we know so far is that by connecting multiple robots together, we can start to use these interactions to be able to get more effective robot locomotion. And what we're looking forward to is in the next, by the end of year 2, we want to show active coordination between 2 or 3 robots that are connected by these trusses. If you click next, long term, and the reason I would be really excited to engage with people at LSIC is we think that there are implications both for multi-robot navigation, where now we can start to access more interesting environments that single robots may not be able to access. But also, because the robots are basically manipulating the ground as they're traveling, we can start to think about how these planners can also engage with passive loads, not robots, as a way to potentially deal with construction sorts of tasks. And so if you go to the last slide then, before I close, I just want to show the team that's been working on this project. This is a team from Penn and USC that's also been supported by a huge number of students who are very interested in this technology. And so we would also like to thank the LuSTR program for giving us the opportunity to work on it.
All right, thank you, Cynthia. Just a reminder, since we're one presentation away from our Q&A session, if you have any questions, please add them to Slido, and you can also upvote questions there. So we'll start after Professor Dreyer.
Okay, thanks everyone. I'm Chris Dreyer from the Colorado School of Mines. So I'm presenting here on MAGMA. I inherited this as the PI. I was on the team from the beginning, but I inherited when Dr. Kevin Cannon had written this proposal and left Mines about a year ago and left the team. So it's a group of Mines professors from space resources like myself, from metallurgy, ceramics, and additive manufacturing, and we're teamed with Lunar Resources to advance an MRE, a molten regolith electrolysis concept. Our NASA collaborators are there from Glenn and Marshall. So what is MRE? This might be something known to everyone here, but it is electrolysis of the molten regolith directly at a high temperature, 1600 Celsius. In what we are working on, we are doing this directly in a vessel. Sometimes there's another form of MRE that's mentioned called cold wall MRE, where the intent is the regolith is, you're really doing electrolysis of a regolith melt pool. In this, the melt is directly interacting with the reactor wall. And so the material compatibility becomes quite important. Our objectives are to produce castable aluminum wire that then can be evaluated for its use as an additive manufacturing material. We're developing taps as a transfer mechanism between reactors and removing the melt from the reactor, the molten metal, and then also a quench wheel to produce the wire. We're doing a variety of things of evaluating the wire and evaluating materials compatibility. The approach here is a lot of this material compatibility, as well as the MRE itself is being done by the team from Lunar Resources. And I don't think we have anyone here from Lunar Resources today, but from the Mines team, we have Ben Schneiderman, who's a postdoc sitting there in the middle. We'll also be showing some of our products here from the work in the show and tell. Ben's work in particular is this area of a thermophysical model using a code called FactSage. One of the concepts here is this is purely thermodynamics, but we produce a kind of reaction variable, the lambda oxygen, which is the fraction of oxygen extracted from the melt. And in this system, we're working with a Highlands simulant. We begin by extracting iron and silicon. Then we reach a point we call the transfer point, where we would extract the iron silicon, and then electrolysis continues, but this is primarily on aluminum. With the aluminum then being a lighter metal, it floats on top of the melt. As iron silicon's heavier, it sits beneath the melt. And then we extract that off. And this study on the thermal physics has guided us on the likely composition of the produced aluminum, as well as the iron silicon mixture, and other factors to be considered. So this slide here is has a lot on it, and I would encourage you to look at a paper we recently had published in Acta Astronautica that Ben led, but shows the composition trajectory as we move through lambda oxygen, just incrementally removing oxygen and seeing how the system reorganizes. And on the right side, the liquidus, the kind of as how the liquidus temperature evolves through the reaction, and the viscosity changes, all of which is very important for understanding the process of MRE. On the table on the lower left, a couple important things here are at the point where we find it optimal from analysis to transfer or remove the iron silicon. It is, you see the composition there. There is some aluminum in that. That is that aluminum begins to electrolyze while there's still iron and silicon present. And then in the final aluminum product, it is more than 99% pure aluminum, but with small amounts of silicon and calcium particularly. And that's actually okay. We'll find that the common alloys of aluminum do have iron and silicon and calcium in them, and you do want a bit of that to improve its workability, although you don't want too much. We've also done, I mentioned already, we've done viscosity calculations from FactSage. We've also looked at that in a couple other ways. We've directly measured the melt and molten regolith viscosity at mines. We have another paper coming out that's going to focus on this with different melts and different reduced oxides. Okay, moving on to material compatibility. This is another area we spent some time working on finding materials that are compatible with the melts and the metals of a hot-walled reactor. There's a number of different things we've looked at. So bottom line is alumina is a good non-reactive material, but we've also found that boron nitride is a pretty significant material that is relatively unreactive. We've also measured wetting angle, viscosity, and resistivity directly of various slags, molten regolith as well. This is a little bit of detail on this. This is melt in interaction measurements, where there's a small bit of regolith simulant melted in a crucible. We then look at the interaction of the crucible wall with the melt, and there's EDS measurements on the right that show the formation of iron within the melt at the wall, penetration of the melt into the wall, and the recrystallization. There's a lot that can be learned from this. In fact, there's another publication coming out that'll detail this. There's a little bit more closely on molten CSM LHT1 with hexagonal boron nitride. There is some reaction. We find this interesting thing that iron spheres develop at the wall. We are doing this in a slightly reducing atmosphere, a little bit of hydrogen in there to extract the oxygen that's being formed. But this has led us to conclude boron nitride is it is reactive, but it's a relatively good balance between non-reactivity and compatibility with a lot of the materials. This is a wetting angle measurement, and I think the two videos that are running on the upper left and right are interesting. On alumina, the molten regolith wets very easily. That cube flattened out. We have a little pressed cube of CSM LHT1 in the upper left. It flattens out and wets the entire surface of alumina. On the right, on boron nitride, it sits as a sphere like you would with a high surface tension material. Some other things going on here from our colleagues at Lunar Resources, where they are building the MRE reactors that we'll be working with there. They have built several different reactors, and they'll be working with various lunar simulants. We'll be working with them of integrating a tap into one of these reactors. We've worked with them to help select the refractory materials that are more compatible with this setup, and this is also an area of work of some testing that should occur, that we plan to have occur in October, or by October. So there are actually two distinct reactors, a extractor reactor, which focuses on the iron and silicon process, and then an aluminum reactor that focuses on producing the aluminum that is going to be integrated with a tap to produce wire. Going on to the tap, this is an area mines is involved in, and this is where a lot of material decisions come into play. We ultimately want taps that can be usable in a variety of situations, from extracting the iron silicon mixture, extracting aluminum, and also a transfer tap that just works directly with slag, partially processed slag, all of which must be compatible to withstand high temperatures, chemical compatibility of this variety of materials, and proper wetting behavior to ensure we have good transfer through the tap. We had initially thought we were going to use alumina. It is the best material compatibility, but actually has a poor thermal shock behavior. And we've done some testing that just when molten aluminum flowed through it, it just shattered instantly. I can show you some of the results of that in our show and tell. So we're moving to graphite, which has poor material compatibility or chemical compatibility, but good shock characteristics, and plan to coat it with boron nitride to protect it and have better compatibility. There may also be some boron nitride parts we'll work with. This is our tap design. There is a plunger there that moves through this the kind of wide joint, or you see from the reactor to the transfer point down to the quench apparatus. All of this is designed to be attached to the Lunar Resources reactor, so the entire system is quite hot. We've done various testing and prototypes and are in the process of testing this with aluminum. The focus here with this tap is on aluminum. There's various foundry tests that we have a nice foundry at Mines where we can melt aluminum, melt a regolith, and pour it through different tap designs. Some of this is just some videos here of that work in the foundry. And we're getting close to the end. The aluminum wire is actually produced here by a quench wheel. This is one design of a typical quench wheel. Lunar Resources producing that, so the Mines tap delivers molten aluminum to this. The temperature of the molten aluminum must be dropped from the reactor temperature down to just above its melting point, and then the wire will be pulled off. At Mines, we are looking at some synthetic wire with compositions produced by the FactSage analysis. And we're seeing some progress here. We quantify this via the point we call the transfer point, where we decide to begin to switch to aluminum extraction, and that affects the residual amount of calcium and iron and silicon in the aluminum. And a few too much calcium, and it's too brittle to pull as wire, the right amount, and it's actually beneficial. So we have at least one. We're expanding the scope of what we're looking at. And that's it, although since this was a panel, which hopefully we'll have some discussion on, challenges in advancing readiness. As a LuSTR project, what we're looking to do is produce technology development that then can be integrated into actual and lunar missions. I thought I'd put a slide here to talk about that. Of course, we're navigating through multiple different types of NASA programs. Many of them are structured around TRL level, from kind of really 3 levels: low, the middle, the mid levels, and then the high. And then we're also often navigating private funding. Like I have a partner who's privately funded, which brings with it some IP and competition concerns. I want to say some other thoughts on certain issues of readiness is that TRL is a factor. So most of the programs at NASA are structured around TRL. TRL presents technology development as if it's linear, but there's some ways of thinking about it as cyclic. I would say even a relatively high TRL system, especially if it never flown before, likely has open questions that really are more of a fundamental science question that still might need to be answered, even if the technology works. And then also there's timing issues. And then moving from one program to the next, there's always, does the next program available to you actually sync up with where you're at? Or is there a gap? I would say there's frequently a gap. At least you have a gap in time waiting for the next proposal to be selected. Sometimes it's advantageous to go to an SBIR, STTR after, say, other STMD programs. But in many cases, you're technically resetting, you're spending a year or more waiting for that to kind of catch up to where you were when you ended your previous program. So those are just some thoughts on that. And that's it from me. And I want to go to
Thank you very
next
much,
phase.
Let's give a round of applause for all our presenters. And thank you for the program comments. We'll definitely take those into account planning for the future. We do have a few questions online. I'll pick the ones that are most applicable to everybody here with the time we have for questions. The most popular one is, was there any special facility that you would have liked to have access during your LuSTR program? If so, what was the barrier to access? And I guess also, if you did create a facility or testing device of your own, would you have preferred to have one that was sort of public use and you could have printed time on, for example, rather than do your own? So sort of two aspects of the same thing about the facilities that you use and any that you would have liked to use but did not have access to.
So I guess in hindsight, it would have been nice to have used a thermal vac chamber rather than trying to get our own functional. I think that we probably could have gone down that route at the beginning of the proposal, but I think we just didn't know what was available at Goddard and how much overhead there would have been to try to get time on that facility and like use that facility. I'm not sure that this is so much a problem of NASA's responsibility as maybe just our responsibility to have explored other options before we wrote the proposal.
Yeah, I guess I've often encountered that there is something out there that would be good to have access to, but knowing how to get access to a facility, how much time it's going to take to actually get there and be able to use it is a bit too high, and it'd be advantageous if there kind of all the mechanisms to get access to something and then were low and easy to work with. I think in a program like LuSTR, 2 years might sound like a decent amount of a lot of time, but it's really not. And so 6-month delay, well, I don't know, any kind of delay just leads to your, as you know, Harri, kind of LuSTR's frequently requesting a no-cost extension. So.
I will also add, I think our research collaborator has been really helpful in trying to facilitate our ability to use NASA facilities. So the survey test bed that we used for our tests, access to that was facilitated through our research collaborator. I think one of the facilities we might have liked to be able to use is there's also a slopes lab where we can also control the geometry of the terrain to be able to create more interesting environments than what we can do at Survey. And really, for us, the reasoning behind figuring out how we were going to test was kind of what Chris was referring to, just ease of setting everything up. Although I think once we have the system in place, we would still be really interested in trying to make those connections and testing on more interesting environments.
Right, thank you. The second question I'll ask is actually directed to Gecko again, but I think it applies to everybody. So what lunar environments were reproduced during your testing? And for those not included, do you expect to see any impact on performance and or lifetime, specifically for Gecko roller, but all of them?
Yeah, so we are doing the ultra-high vacuum testing, and then we're doing thermal testing down to about -60 C. We haven't done either of those testings yet, but we're planning to do that this year. In terms of what environments have we not included in our testing, is we haven't included any plasma effects or like charging of the dust due to interactions with plasma or due to some controlled tribocharging that might occur. So those are environments that we haven't explored. I would imagine that the charging of the dust may make the EDS more effective. It may also make the dust stick to the Gecko roller a little bit stronger. Kind of unknown.
Cynthia, want to go next?
Sure. So the sorts of environments we've tested on are basically so far flat maps of LHS1 with ranges and stiffness with the largest range of stiffness that we can achieve with our machines on campus, and then manually with shovels and tampers at Survey. We have not looked at the effects of low gravity, which I think would have an impact on some of our results. And then the other thing that we had originally proposed, but we haven't looked at a lot yet, is what happens when there are also ice particles in the mix.
For us, the aluminum reactor and quench wheel will be, with the tap, will be tested in a vacuum chamber. That'll be at, it's in the -5 torr. So the interior of a reactor, of an MRE reactor, is at pressure, at an elevated pressure, so you have to keep that contained. It is, in fact, actually the process seems to be sensitive to the temperature, or sorry, to the pressure you operate at, so you wouldn't have an MRE reactor. You may not want to have an MRE reactor open to the lunar environment. You'll be evaporating a bunch of metals that you might prefer to have captured. There is an open question about whether, as you do the quench wheel with with aluminum in the lunar environment directly, that the aluminum and maybe some of its components will be evaporating away, and that's really a matter of how quickly you can quench the material. So, but we're testing that inside of a vacuum chamber in a lunar resources lab, and that's how we deal with the lunar environment.
All right, thank you. I think we're out of time, so thanks again for the panel. If you have questions to the individual researchers, please feel free to contact